Okay, so for this video presentation number 3, I have a combined loading problem. For the beam shown loaded below, find the principal stresses and the maximum shear stress at point A. Use the coordinate system shown, and here it's just telling you that this is aligned with this force, the Z is aligned with this force. So when you want to solve a combined loading problem, you want to start out by having a transverse cut at your point of interest. So the point of interest here is A. So I want to do the transverse cut this way and disregard everything behind A, behind this point. You're going to forget that, and I'll draw it again. So from there I can draw the free body diagram of the reaction forces and the reaction moments. So then I'll just have it here so you can see. I'll just draw this section. Okay, that is meant to be to scale. Okay, have that. Then this is, because we're forgetting about the 24, it'll just be 180 from here to here, 180 millimeters. This is 40 millimeters. And then at point C, it's the middle, have 500 newtons, 10,000 newtons, 10 kilonewtons. And like I said, you want to have your origin at the free body diagram right at the center. So this is behind the picture, so you guys can see it. The free body diagram should be at the origin or the center of this, so then you can determine your reaction forces, your reaction moments. So this is Ry, reaction force in the y-axis, Rx and Rz. And as you can see, this is aligned. If I put it in the origin, it's aligned with the 10 kilonewtons, and same thing with the Z force, the reaction force at C. At Z, it's in the same point, in the same elevation, if you will, on the y-axis. Okay, and then let me just have this again so you guys can see it. This is Z, which I'll be using it in a little bit. Z, and this is Y. Okay, and now that I have my reaction forces, what is the reaction moments? Well, just by as a general rule, you have your rule of thumb, your fingers pointing to the direction of the axis, and your thumbs are going around this way, and that's going that's telling you your positive reaction moment. So this is going for the z-axis. It's going, let me just have it, it's going this way. It's going kind of up and then around on the top. MZ, is that right? Yep. And then same thing with the RY, the MY, I mean, it's going this way for the positive reaction moment. And same thing here, but this one is going kind of to the left, MX. Okay, now how do you find the reaction forces and the reaction moments? Well, you want to start out by having a table with the organized data. Oh, and by the way, I've missed one number here. This is a 750 Newton force going down, and it's on the top of this surface. Okay, so then if I make the table, let's start out with 10,000 newtons. These are the loads. Loads. This is the R vector. This is telling you where your force is at. And we're going to have it in Cartesian form, so I can find the moment. Okay, so this is I, J, K components. I, J, K components. And this is loads. Let's start with 10,000. 10,000 newtons, then the 500, and then the 750. Okay, now, like I said, I want to have this as a reference. So, because I've always been used to seeing, you know, this one being the X, this one being the Y, and the elevation being the Z. I want to stick to having the X as the I component, the Y as the J component, and this one as a K. I'm used to seeing it in that form. So I'll just, instead of assigning the Z with the K, I'll assign it with the J, and the X with the I component, and the Y with the K component. And then here again, I'll just make a little note so I won't, you know, swap, you know, screw up the data, having it backwards. So here I have this one stays as X, so Rx. This one, instead of being Ry, it's going to be Rz and Ry. Same thing here. This one stays at Mx. This one stays at Mz and My. There you go. Just a little note for myself, so then I can go back and look at which one I chose, which one to choose from. Okay, so where is this? Where is the 10,000? How long does it take me to get there in the x-axis? In the x-axis, it's 180 plus 40. It's 0.22 meters. And the base unit here is meters. Base unit is newtons. And then Newton meters. And then 0, because it doesn't move in the Z and the Y direction. Same thing with the 500. How long does it take me to get there? It's just 0.22 in the x-axis or the I component. And then 0, 0. Well, this one is actually, I get there a little bit earlier, so 0.18 in the positive X. And then in the J, it does not move. This is the, let me draw it again. Rx, Rj. Yeah, the J does not move anything, so it's 0. And then the K, it moves up just a little bit above because they give us a thickness of 16. I mean, from the center to here, they give us, this is just 16 millimeters. So it'll just be 0.016. And that should be right. Let me see if I screwed up the numbers. 16, 1, 2, 3. Yep. Okay. And then now let's go with the forces. The forces here are, let's start with the F. It's given, and it's going towards the I component, 10,000, 0, 0. And then the 500, where's the 500 going? It's 0. And then it's going with the Z axis. So this is 500. Okay. Yep. And 0, 0, 0. And the Y is negative 750. Okay. Then same with the moments. Now, how do we find the moment? Well, from statics, we learned that earlier. And it's just the moment is equal to R cross F. R cross F. And I'll do it in the calculator in a little bit, but I just want to show you, if you don't already know how to do a cross product between two vectors. Well, you have this setup, I hat, J hat, K hat. And let's say you have two vectors with constants A, B, C, and D, E, F. So this vector cross D, E, F, general rule is you have I component times BF minus EC. Whatever you get is your answer. And then for the next one, minus, and let's do this one, minus this one times AF minus DC. So it's actually J times, and then all of the result here, AF and minus DC. That's your answer. And then for the last one, so it's easy to see, plus, it's going to alternate. So if you had more terms, it's going to keep alternating between a plus, minus, plus, minus, plus, minus. So I have plus the answer of K times AE times DB. Okay, but I'm going to do it in the calculator, and I'm going to start by naming the vectors. And I have this. Let me clear the memory. So, because I did it before and don't want to screw up. Yes, okay. Now, vector A, I'll define it as this vector. Oh, and by the way, I'll name this vector A as 0.22, 0, 0, and vector B is going to be, and that's just another way with this, the arrows having as a vector. It's just another way of writing it instead of having the IJK. Okay, now that I did that, I do A cross B, and that should be the cross product. So then again, 0.22, 0, 0, done. Then vector, I'll name vector B, define it as 10,000, 1, 2, 3, 0, 0. Okay, go to menu. Where is that? Vector cross product. A comma B is just telling you it's a cross product, A cross B. And I get 0, 0, 0. That is just 0, 0, and 0. Okay, let's see. So if I have this one, 500, I'll name vector B as 0.22, 0, 0, and vector C, this is vector C. Vector D is 0, 500, 0. There you go. And C cross D, again, define C, 0.22, 0, 0. Vector D defined as 0, 500, 0. And C cross D, once again. C comma D, and I get 0, 0, 110. So then here, what did I say it was? Well, 0 is the I component, the J is the, this one. Well, it's already aligned, so I just plug in here. I don't need to flip anything. Okay, let's see. And the last one, 750. Just draw it here. Let me just a little bit shift it. There you go, 750. Well, it'll just be vector E defined as 0.18, 0, 0.016. Vector F, I'll name it 0, 0, negative 750. And when I do E cross F, what do I get? I get, once again, the last one. Define E as 0.18, 0, 0.016, and vector F, define it as 0, 0, negative 750. Okay, and the last one. E comma F, and I get 0, 135, 0. And again, I just plug in here, and there you go. Now, I found these reaction forces. I found the forces and the moments that are acting on the rectangle, but now I want to find the reaction forces. So the reaction forces and the reaction moments are opposite of what I found. Why? Because if I add all these up and I add the negative, it's going to give me 0. This object will not be moving, and so if I have a resultant force, it's not gonna, that is 0, it's not gonna accelerate, so it's just static. Okay, and then RZ, and then MY. So, okay, let's start with the F. F is just 10,000 plus 0 plus 0. It's gonna give me 10,000. Minus 10,000 is gonna give me 0, so it's just minus 10,000 newtons. Okay, RY, go to this one, and it's 750 positive. And then RZ is negative 500. Okay. So there you go. Okay, for the moment of X, I add up 0 to 0 to 0, I get 0. And then for the MY, it's negative 110, opposite of 110. And 135, 0 plus 0 plus 135 is 135. So it's negative 135 Newton meters. Okay, now I can do the stress blocks, so that then I can add all of the stress blocks. I do all the stress blocks combined, and then plug into the principal stress formula to find, what is the maximum stresses I can have on every possible plane through a point A. Okay, let's see. So then again, let's start with Rx. Oh, and by the way, before I continue, I want to recognize in this problem which one is the longitudinal direction. That's important, because if you don't know which one that is, and you're not going to understand which one is your lateral direction, then you have to look at the moments and the torsions that you need to find out in the problem. So the longitudinal direction is just, it's going to this rectangle is going towards the x-axis. So that's the x-axis. So this is the longitudinal direction. Okay, and then another thing, what is your longitudinal direction viewing angle? Well, how do you look at it? Well, you look down this this rectangle, and you're gonna see it's about the ZY plane, and that's gonna be important in a little bit, because we're gonna always, if it's lateral direction, you're gonna want to look at another direction that is not this one. So this is longitudinal. Okay, now let's start. Finally, if I have a force in the longitudinal, it's going to be an axial stress, and to find the axial stress, you look at either lateral direction. So let's start with sigma x. And what is either lateral direction? Well, we can find any other, we can look at it at anywhere except zy. So how about we look at yx? Let's try yx. So I have this as y, this is x, this is the cut that I do, and this is the rectangle. Okay, now where is point A? I had point A here. So point A is in the y, so it's going to be right at the top here, this little square. Okay, so it's defined as P over A, where P is your load. A is the area that the force is on, so it should be this area that we can't see here, that's going into the z-axis. So then, if we think about it here, this is if this is the rectangle here that we have, the object, and this is the yx, this is a block that we drew. Well, it's, let's see, Rx is a reaction force. So Rx is actually this way. Now, what did we find in Rx? We found that in Rx it was negative 10,000. So this is y, this is x. It's not going towards the positive x-axis, but negative of that. So it's actually kind of pulling it this way, 10,000 newtons. Okay, now what is happening with the little rectangle here? The little rectangle is in tension. So I have 10,000, and then the area, well, it's just this area that we mentioned, that it's being stretched. So we're given that data, and where is the there it is. So let's find this whole area. What is that? It's 0.032, that's double of this, times the base, and the base is 0.06 meters. Okay, oh, I can actually just put it here, 0.032, 0.06. Times 0.032 times 0.01, oh, not 1.6, and I get, oh wait, I forgot to divide. I multiplied everything. So 10,000, now this, yeah, there you go, divided by 0.032 times 0.06, and I get 5.20833 times 10 to the 6 pascals, because it's a force over a squared area, I mean over a squared dimension, so it's area, and I get that. Now the next step that we're going to want to find is what is the stress blocks that is happening from the axial stress. And by convention, you have 3 stress blocks, and you have this is the XY plane, this is your stress block, your block that the stress is being applied on, this is the XZ, and this is the ZY. Okay, we found that it was positive 5.2 times 10 to the 6 pascals, and so what is happening there is it's just stretching this little square that much. So it's going towards the X, yep, as you can see there, and away from, and crossing the Y. And then the XZ, let's think about the XZ. If we have the XZ plane here, this is my stress block, this is Z, this is X. Well, we found that it was stretching this block going this way towards the X direction. So if we just turn around the picture, we can see that it's just going to go this way. Oh, it's just going to go this way. And the result will be for both 5.20833 times 10 to the 6 PA, pascals. Okay, done with the first one. Then the next one. Let's see, we found it was mx. And when you have a moment, reaction moment, about the longitudinal direction, you're gonna want to use a torsion formula, and the formula for torsion is just tau is equal to T rho over J. Now here, the reaction moment is just 0, so at T here we're gonna have 0, so everything will just go to 0. And again, if we have 0, then we're not gonna really be able to do any stress blocks. Okay, done with the second one. Ry. Now, because I established this at the beginning, that X is the longitudinal direction. Now we're in the lateral direction. Let's go with a force, a reaction force of 750 newtons. The lateral direction will give me, when you have that in the lateral, you're going to want to look at the transverse shear stress here. So what is the formula for transverse shear? Well, it's just tau equals the shear force times Q, where Q is the first moment of inertia, and it's just a measure of the distribution of the area about the neutral axis. And well, Q, but how do you find Q? Well, Q is just y bar prime times the area, and what did I say? It was IT, and I is the area moment of inertia, or also known as the second moment of area, and it is just a measure of the cross section resisting the rotation or bending about any axis, and that axis can be the neutral axis. So you'll see it in a little bit. So if I have, now what is the viewing angle for this one? You're going to want to look at the lateral direction the force is not acting in. Okay, so lateral direction, it can't be this one. It can't be the ZY. And let's see, where's the force? RY. First, locate RY. It has to be going towards one axis. So if we look at YX, let's see, YX. The force has to be going, what is telling you that the force can't be acting on the plane? It means this, that if I chose the other lateral direction, the YZ, oh no, not the YZ, the ZX, for example, if we chose this ZX plane, then the force RY would be going on the plane, either in tension or compression, and that's what we don't want. We want to have it in line towards either axis, and that's what we have here. The force RY is going up. That's positive, but we found earlier, yeah, it's going towards a positive because it's 750. So this will just be 750 newtons. That's a shear force, and this is my cut. Yep, that's my cut. And let's see. Now, where is point A? If I have YX, you can kind of see on the image here that this is just flipped. This one is going this way on the, the x-axis is going the other way, but still the point A is on the top here. Okay, now let's see. We found that out. So when we plug in everything, we get 750. But then let's find Q. What did we say it was? The first moment of inertia. And the first moment of inertia, y bar prime, is just the centroid of the top half. And this is the neutral axis, like I said before. This is the neutral axis that your area distribution, measurement is based on. This. So let's see, the area above the point of interest, and the area above your point of interest is nothing because it's outside of your object, outside of the the rectangle object. So then here it's going to give you 0, and that makes sense because your maximum transverse shear should be close to the middle, like right at the middle. And as you get out of the middle in either direction from the neutral axis, then it's going to get closer and closer to 0. Here should be 0. And here you have just a parabolic function that tells you how much your transverse shear is. So here should be maximum, here should be 0, because the Q, the area above, is just 0. So everything goes to 0. Okay, that was easy. And let's go for the next one. Let's see, we're done with this one. Let's go to MY. And once again, you don't have any stress blocks because, you don't have anything to, either have tension or compression or any shearing force. Let's see, My, yep, My, and we found that it was negative 110 Newton meters. Okay, and when we have a lateral direction moment, you're gonna want to look at bending moment, and that bending moment is going to create a stress on this part. So let's see, the lateral direction. So for this one, you want to look down the axis the moment is acting about. So if we locate my moment, where is it? My moment is here. And if you look at this one, where is it acting about? It's acting about, if we just maybe expand this a little bit more, it's acting about the ZX plane. Yep, and let's draw it out. This is X, this is Z, and this is my cut. This is a part of the rectangle here. Okay, now where is point A? Well, point A, it looks to be in the middle, because if you kind of look at it here, you're doing a cut about, this is the neutral axis, this is a middle, so your point will just be right at the middle. And what is the formula for bending moment? I think it's just sigma. The stress from the bending moment will just be MC over I. But now here, let's think about an example for a little bit. If I had my point here, then the moment that we found, and what is the moment? So it was negative 110. Where's my picture? Here's the picture. My, so it's opposite of this. It's going to go this way, and it's going towards from the Z to the X. Yeah, from here, if we just continue the arrow from the Z to the X, it's going to go this way. Yeah, that's a 110. Because I flipped the sign there. Now, if I had this point A being on the top, then I know it's going to be fully in tension. And if it were here, then this moment would be compressing this little point. So now, because it's right at the middle, it has both the tension of the moment and the compression on this one. So it's just going to cancel out to give you 0, because it's right at the middle. It's both being in compression, so they both add up, they give you 0. Okay, that's easy. And then once again, you don't have any stress blocks. What is the next one? The next one, we're done with that. And Y, RZ. Let's look at RZ. RZ, you have, once again, a lateral direction. So you're going to have a transverse shear stress here. Oh, not stress. You have a shearing stress. So you have, what is the formula? Tau equals VQ over IT. And let's look at the picture. So lateral direction, the force is not acting in. So if we locate RZ, okay, it looks like if we choose the other lateral direction, YX, it's just going to go into that plane. So let's choose ZX once again, because it's not acting on the plane, but it's acting parallel to, oh, there you go. It's acting parallel to one of the axes. And what we found, it was negative 500. So if we know that this is positive, it's going to go, that's a cut. It's going to go down 500 newtons. Yep, okay. And Where's point A? Well, point A, same thing. Now we found that it was here in the middle. That's what we found earlier. Okay. What's next? Let's see. Well, we just plug in 500. And then Q, what is Q? Q equals y bar prime times the area. And y bar prime is just the centroid of this, of the top half or the bottom half. In this case, you can pick either one, but I picked the top half. And what is its dimension in the z? It looks like this is half of 60, which is 30, and half of 60 is a centroid, because we're looking at this point. We're looking at where the centroid of the of this top half is. So it's just 15 millimeters, so which is 0.015. Then the area, well, the area of the whole thing, I think, yep, the area of the, I'm sorry, of this top half, because it's above this little point A, the area above that. So what is that? We said that this is half, so 0.03, and this, the x length, the x base, is just going to be from here to the end on the x-axis. So it's just going to be 0.22. Okay, pretty easy. Now we just multiply it out. And what do we get? Well, let's just see it here. 0.015 times 0.22. And then I, well, I is the area moment of inertia of a rectangle. And this rectangle, you have to find it, well, it's formula for the rectangle, BH cubed. Now B is the base, 0.22, it's a, this long part, long distance, and H is 0.03. Oh, no, it's not 0.03, it's of the whole rectangle, I'm sorry. So it's 0.06 for this one. So again, you plug in 112 BH cubed, base is 0.22, height is 0.06 cubed, and we end up getting, let's see, yeah, as you can see there, that's what I did. Okay, let's see, 1 divided by 12 times 0.22 times 0.06 to the third power, close the parenthesis, I get 0.0000050 zeros and 4 times the thickness, and the thickness from the neutral axis in the z direction will just be 0.03. And now I can plug in everything to the calculator, and let's see what I get. 500 times 0.015 times 0.22 divided by 0.02345, 4 times 0.03, and I get 1.37. Is that right? Did I do it right? Let me try it again, because earlier I got something else. Times 0.015 times 0.22 divided by 1, 2, 3, 4, 5, 4 times 0.03. Okay, well, I get 1 point negative because this is actually going down. The shearing force is down. I almost forgot about the negative sign. So I end up getting negative 1.37 times 10 to the 7 pascals. Now, what does that mean? It means that the this what do you call it? The transverse shear will be maximum at this point. So it will be this value here. And again, I need to draw this 3 stress blocks because finally I got an answer. So what do? Let's see. I go from here. Oh, no, never mind. forgot the usual way it goes. It's actually this way, xy, this is xz, and this is zy. So I get a negative, and it's only acting, here the tricky part is, it's only acting in this plane because this infinitesimally small point, think of it as a little square. It's acting on this surface of the xy, of the xz plane. So the only way it can go on this shear stress is in this plane, in this stress block. So it's going to go this way, negative z and negative x, and then just follow the arrows towards it, and you get the result 1.37. I can drop the negative sign, times 10 to the 7 pascals. Yep, and we disregard these because, like I said, it's only on this, it's only lying on the xz plane. Okay, last but not least, I think we need one more. Where is it? It's here. We're done with this one, and the last one, we need to find the the reaction moment. So you're gonna want to look at bending moment, a stress that the bending moment creates, and you look down the axis the moment is acting about. So again, looking at my. Where's my? My is acting on which plane? On the zx plane. If you look at this, my, and it's negative, so it's going to go actually this way. That's a positive moment, so we get a negative, and it goes from the z, if we were to continue the arrow, it goes from the z to the x. So once again, so you guys can see it. It's actually, let's see. So we said it was a zx. This is my cut. Yep. So we said this is opposite of that because we got negative 135 from the z to the x. Yep, and it should be like this. And like I said, what we found earlier, we found that it was, let's see. It's acting about the zx. Just 1 second. Okay, well, it looks like this one, and we found that earlier from the other planes. XZ, point A is at the top. Point A is at the top. Let's see. No, not the top, sorry. I'm just trying to see this. Better light. Oh, it's actually in the middle. So once again, the bending moment. Will it just be 0 again? Looks like it's going to be 0 once again. Where did I mess up? Look down, the axis the moment is acting about. Oh, no, I'm looking at the wrong one. I thought this was a Y, this is a Z. Jesus Christ. Alright, so disregard everything here. This is not the result. Look down the axis, the moment is acting about on this one. So if we're looking at the Z moment, it's acting about the YX. So let's draw it again. Whew, that was close. MX. Okay, and it's acting about, if this is positive, we get a negative. So this is positive, so we get a negative. So it's going from the x to the y, from the x to the y. Okay, I think that should be right. So you guys can see it once again. This is the mz, this is y, this is x. Let's see. Look down, the moment is acting about, the plane the moment is acting about. So this one is z. This one is going this way. So opposite of that is this way, from the x to the z. Yep, that should be right. And where is point A? Point A is at the top. So finally we're going to find an answer here because it's not at the neutral axis like before. So then what was the answer that we need to plug in? mz, bending moment, formula is sigma z is equal to mc over I, where m is 135. We take off the negative sign because we flipped the direction. And now, as you can see, it's being here compressed. The moment is compressing this infinitesimally small block point. Oh yeah, block here. This infinitesimally small square. And so 135. So it's going to be in compression. So we get a negative 135. Then the thickness, C, if we look at XY, what is XY thickness? It's this one. It's this segment here. So it's 0.016, 0.016. And then I, we found that earlier for the area moment of inertia of a rectangle, 1/12 bh cubed, 1, 2, 3, 4, 5, I remember, 5 zeros and then a 4. And then when we plug in everything, what do we get? Let's see, negative 135 times 0.016 divided by 1, 2, 3, 4, 5, 4, and I get negative 54, 1, 2, 3, 4. Negative 540,000 Newton meters. Or no, just pascals. PA. This is a force. This is a stress, I mean. Okay, that's it. And now that I found every single one, every single reaction moment, and every single reaction force, every single reaction stress and reaction shearing stress. Now I can combine them all in one of the three stress blocks, and I combine them. And let's see. Let's just go back and make another one. Stress blocks combined. Okay, XY. X. Nope. This is X. Z, and this is the Y. Okay, so for the first one, let's see. Did we find an answer for the very first one? Let's see. We got 5.20833 on the axial stress times 10. For the axial stress, I found 5.20833 times 10 to the 6 pascals. For the XY and the XZ, XY and XZ. And then let's see if I find another stress. No stress. No shearing stress. So it appears I just have two stresses. So I add them up, and I get a tension, positive 5.208. 5.20833 times 10 to the 6 okay, plus, oh no, not plus, but minus this answer, minus 540, 1, 2, 3. And I get 4.66, still in tension, 4.66 as a resultant stress, 833 times 10 to the 6 PA. And then let's see if I have any other shearing stresses. 0, 0, and the last one, it appears I just have 1, which is 1.37 times 10 to the 7. And it's going this way, going this way, going this way, and going here. That is the only shear stress that I have. So 1.37 times 10 to the 7 PA. Okay, now that I have all the results, I can finally find the principal stresses and the maximum shear stress at point A. And so you want to look at, if I had more numbers here, you would just look at which one has the most to pick either the XY or the XZ or the ZY. So obviously there's nothing here, there's just the 4.66, but it's also applied here. So in the maximum, it's just going to be 4.66. And let's do this again. So what is the formula to find sigma 1 and sigma 2? So principal stresses, sigma 1 comma sigma 2 is equal to sigma, and because this is the one that won, if I had, like I said, if I had another one, let's say that this one had a shearing stress of a bigger value, then you would pick this one, and then disregard this one to pick for the XY. I mean, to pick the sigma X and the sigma Y instead of the sigma X and the sigma Z in the formula. You'll see it in a little bit, what I mean. So here I have sigma X plus sigma Z divided by 2 plus or minus the square root of sigma X minus sigma Z divided by 2, you square that, plus shearing stress XZ squared. Yeah, so what I mean is, if I had, let's say, a bigger number here in the shearing stress than this one, then it would be, instead of XZ here, it would be, let's say, XY. That's what I meant. Okay, and then what do I plug in? Well, sigma X is just the tension component. So 4.66833 times 10 to the 6 plus 0, because in the Z direction nothing happens here, it's not being stretched or compressed. 0 divided by 2 plus or minus, and same thing, 4.66833 times 10 to the 6 minus 0. Oh, there you go, you can see that, divided by 2 squared plus 1.37 times 10 to the 7 squared. Yeah, and here, why it doesn't matter which one you pick. You pick the one with the largest magnitude, so it doesn't matter if it was a negative or a positive, because here, that's where you square it. That's why it doesn't matter. Okay, and let's see. I think I'm done with that. Now I can just remove this and plug into the formula. So let's see. I already have it here. Divided by 2. 2.33417 times 10 to the 6 plus or minus and then you got that result. Yep. Then you square it. Okay, and then you add Oh wait, I'm not gonna add it right now. So what if I get 1.37? Let me look for that number. 1.37, 375 actually. 375. Square that. Plus what we found right now, 5.44. And then you take the square root, the answer, and all of this, plus or minus 1.39467 times 10 to the 7. Let me just make sure one more time. 4.66833 times 10 to the 6 divided by 2. Okay, and square this, plus 1.37 times 10 to the 7. Yep, I get the same answer, just confirming. So 2.33417 times 10 to the 6, sigma 1, comma sigma 2. And so sigma 1 will be the largest, sigma 2 will be the least. And what happens when I do that? 2.33417 times 10 to the 6 plus 1.39467 467 percent to the 7, and I get sigma 1 is equal to 1.62809 times 10 to the 7 pascals, and sigma 2 is equal to 2.33417 times 10 to the 6 minus 1.39467 times 10 to the 7, and I get negative 1.16125 times 10 to the 7 pascals. And those are my answers. Now, from there, I want to graph it. So I have this paper here. I want to graph the result in my Mohr circle graph here. So if I have, let's say, this is so tau is the shearing stress. That will be on the y-axis, and it's in pascals. And sigma is your stress, pascals as well. Okay, let's see. So let's have this a little bit easier to see. 1.6209 to 809 times 10 to the 7. No, it doesn't give me. I wanted to give it to me in MPa. I'll just move it 1. So, yep, so it should be 16.2. I just move it 1 spot for MPa because I'm gonna have 16.2809 times 10 to the 6 PA, and that will give me in, this is just 16.28 MPa. So then if I do the jumps, let's say I do, well, let's find the other one first. So it's the scale. So here I move it down 1 spot, get 11.6125 times 10 to the 7, times 10 to the 6. So it's just going to be 11.6125 MPa. and this is actually not pascals but MPa and MP and megapascals. There you go. Okay, and I want to make the jumps. See if I can make the jumps by 1. 1, 2, 3, 4, 5, 9, 10. Now I'll do it by 2. I'll do the jumps by 2. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. Oh, damn it. And there you go. Now let's see. So we found that this one is actually negative. So if I want to graph this, where is sigma 1? Sigma 1 is 16, 14, 16, 18. So 16.2 is right around here. That is the maximum principal stress that you're going to have, right around right there. And then 11.61. So this is 2, 4, 6, 8, 12, 10, 12, 11.6, or closer to the 12, right around here. Now, how do we find the radius? Well, the radius is just actually this term. Tau max is the radius, which is just that. And that is 1.39, I think. We found that earlier. And 1.39. So if I subtract 13.9467 from this, I will get the radius. So let's see, just to be exact, 16.2809 minus 13.9467. So my radius should be, wait, is that it? Oh yes, so this is where I'm going to find the origin. That's why I did it. This is the radius. I've subtracted I do principal minus the radius, and I get where the origin is at. So 2.334 is right around here. This is 3, right around there. And then I get this simple tool to make things easier for myself, because we already know the radius here. So there's no need to really do anything else but to just find this and go back to the either principal stress, and the radius should be the same. Yep, it aligns perfectly if I try to flip it. And as you can see there, it looks like it is the same. Oh, it ended up moving it. Ah, come on, I keep moving it. Sorry. Well, you get the point. The radius is the same. I just ended up breaking the paper. That's why I kind of screwed up a little bit. But it is actually the same. So that is tau max is here. Principal stresses are where? In any single point on anywhere on the plane. On point A, on any plane, on the XZ, on the XY, or the XZ, XY, and the other one, I'm sorry, it should give you the maximum stress here. The maximum stress, let me just confirm it, 16.2028 megapascals, negative 11.61 pascals, MPa, I'm sorry, MPa, that's this one, that's this point, and this guy, tau max, maximum shear and stress, will just be your radius, which is 13.94 MPa. And there you go. That's the answer for the problem it was asking for us. It was asking to find the maximum, the principal stresses, sigma 1 and sigma 2, and the maximum shear stress at point A. And that is the answer.